one proof is for the pointwise convergence, another proof is for uniform convergence. Okay. Well, you may ask me why there is no proof for the L2 convergence. The answer is that it cannot be done until we have learned real analysis. Okay. So let's assume that the L2 convergence is something that we already acknowledge. Okay. And yeah. So these are two things. There is another thing that's called the Gibbs phenomena, and but I think this is rather this is not so directly related to us. Okay, but the Gibbs phenomena, that which is the materials, specifically on page 142 to 144. Okay, and this actually very nicely, this is actually very nice computational, or I mean something that's very nice to read with a very strong computational flavor. Okay, if you're interested in that, I actually encourage you to read that part. Okay, so now first let's get started. So let's say we are looking into a function. Okay, so in this case, let's just simply begin. Okay, with the, because we see we have so many different boundary conditions, right? We're facing so many different boundary conditions, and the and both the pointwise convergence, the uniform convergence, actually the only requirement on the boundary condition was that we just need the boundary condition to be symmetric. We just need the boundary condition to be symmetric, and that actually makes these both theorems to be pretty bored, to be pretty bored. So to reduce the difficulty of presenting the proof, we are going to prove the pointwise and uniform convergence. Okay, we're going to prove the pointwise and uniform convergence for only for L2 from negative L to L, and with periodic. With periodic boundary conditions. With only periodic boundary conditions. And more specifically, you see, we will be directly replacing the negative L to L from negative pi to pi. Okay, and I'm going to argue that for any L, we will just need to compress or stretch the function therein, to finish the proof. Okay, so we'll be just so this is actually, although we are posing limit on L by taking L to pi, actually we're not losing any generality over here. Okay, so more specific from negative pi to pi, and therefore we'll be dealing with the Fourier series. We'll be dealing with a very specific type of the Fourier series, which is the full Fourier series. So that is to say, now let's say I'm having my fx, I'm having my fx, and its Fourier series is represented as 1/2 a0, and then plus the sum from n equals to 1 to infinity, and then an cosine nx, and then plus bn sine nx. Okay? So now will be prove the theorem 1 that will be proved is that when fx is a C1 function. What does it mean by C1 function? That means that this function is continuous. And has continuous derivative, first order derivative. It also has continuous first order derivative. And don't forget, since we are having a periodic boundary condition, that means that this function is continuous after we expand, okay, this periodic function to the whole line. Okay? So that means that, so let's say in certain period is something like this, okay? And when we are expanding this to the whole real line, this pattern is going to appear and appear and appear again and again, right? Okay? And that means that not only is this function is continuous and has continuous derivative from negative pi to pi, it is also continuous and it has continuous first order derivative at this point, pi. Okay, it's also continuous and has continuous derivative on the boundary. So which means that the right derivative over here should equals to the left derivative over here. Okay, so that is the specific requirements. So when fx is a C1 function, let's prove that. Okay, we are going to prove that. So we first prove. Okay, sorry. We first prove that x. We first prove that. Okay, so 1/2. So why don't I just call this guy to be my fn? Okay, this is my full. Let me put in this one. So this is actually my f infinity. This is the whole sum of the Fourier series, and more specifically, I am defining fn to be from 1/2. Okay, a0 and then plus here m from 1 to n. Okay. I'm truncated at the first n terms, cosine nx, and then plus n sine nx. Okay? Again, f infinity indicates the whole Fourier series, and fn is the truncated Fourier series for the first n term. For the first two n plus 1 terms, but it doesn't really matter. Okay, now we will be proving that, okay, fnx, okay, we'll be proving that, okay, when n goes to infinity, fnx, it converges to fx, okay, for any x. Again, what type of convergence is this? What type of convergence is this? For any point x, when n goes to infinity, fnx converges to f. What convergence is this? Pointwise. Okay, it's not uniform because we know nothing about the corresponding speed of the convergence on every point. Okay? So, again, this is pointwise. Okay, pointwise convergence. And that's and you see the pointwise convergence is the goal of the pointwise convergence is actually very straightforward. We just need to prove that, okay, I'm now just simply choosing certain x. It can be anything. It can be any x between negative and positive. I'm just choosing an x. And I'm going to show that the sum, okay, now I'm going to show that the sum of this series converge to a certain number. Okay, and now we are going to argue, okay, the convergence of a series of sums to a certain number. And don't forget. So again, let me write the fn again over here. So my fn, okay, again equals to 1/2 a0 and then plus the sum n equals to 1 to n an cosine nx and then plus bn sine nx. Okay, we want to show that this guy goes to fnx. Okay, we want to show that this guy converges to fx. This is our goal. We don't know it yet. Okay. Well, again, what is my an and what is my bn? What is my an? What is my bn? What is my an? What is my bn? They are the Fourier coefficients. How do you compute the Fourier coefficients for a periodic function on negative pi to pi? My an is actually what?
1 over L.
1 over L. What is L now?
2 over 2 pi.
Okay, 2 over 2 pi L, right? Okay, but again, what is my L? What is my L now? Now it's pi, right? So my an is essentially actually 1 over pi. 1 over pi from negative pi to pi f y cosine ny, okay, dy. This is my n. What is my bn? My bn is again 1 over pi from negative pi to pi fy sine ny dy. So that's a bit. Okay, so now we are going to, okay, you see, now we are going to replace the an and bn by these two expressions. Okay, because of what? Because you see, in this Fourier series, cosine x, sine x, these are objective. These terms are objective because they will be staying the same for any choice of f. For any function, they will be the same. We'll still be using the set on orthogonal basis, right? But where is the which terms contain the information of x? It is exactly these coefficient terms, right? It is exactly these coefficient terms that contains the information of f. Now you see, we would like to prove that this sum converges to f. So we indeed need to reflect the information of f inside, okay, the sum of the formulas. Therefore, we would like to rewrite the an and bn. We would like to replace the an and bn by their definition because these things, you see, it indeed include the f over here, right? It indeed include the f. We would like to have the information of f represented in the Fourier series. So, okay, this is going to be. Okay, so this is going to be, okay, so this is going to be, first of all, the A0, okay, A0, 1/2 A0 is essentially, 1/2 A0 is actually from negative pi to pi, you see, there's actually 1 multiplied by Fy, right? That's actually, sorry, 1/2 over 1 multiplied by Fy. So it's good. And the other terms, okay, now the sum m from 1 to infinity, m from 1 to n, okay, this is essentially, okay, again, the integration pi from negative pi to pi, okay. So first of all, I'm going to get out the 1 over pi over here. And then Fy cosine my, okay, and then multiply by cosine nx, right? And then plus, okay, and then plus Fy sine my, and then sine nx. Well, this guy, and then dy. Everything is the same. I'm just simply replacing the an by the integration 1 over pi Fy cosine y, and there here's the 1 over pi, right? And then this integration actually, the variable is 1, okay? So and multiply by cosine nx, I just simply copy cosine nx over here. So good. So good. You see, the first term is an integration. The second term is also an integration. The first term contains an Fy. Here it also there's an Fy. Here is also an Fy. So what I can do is that there's actually, first of all, the integration, all of these integrations can be combined into one. Okay? They are all integrations from negative pi to pi. And second, inside this integration, there's a common factor Fy. There's Fy everywhere. So I'm going to extract Fy. So I'm going to extract Fy, this is the common factor as the first term. And now the second term, first of all, here's going to be, actually Fy over 2 pi. Okay, Fy over 2 pi. Because there's going to be a 1 over pi, and here is a 1 over 2. So I'm going to extract both of them. Okay, 1 over 2 pi. And then the first term is going to be, the first term is going to be, sorry, here, I think here is still a pi. Okay, The first term is going to be 1 and then plus 2. Okay, sum n from 1 to big N and then cosine my cosine nx and then plus sine my sine nx. Okay, and then dy. Again, this is my big Fy. This is what big my f and x. Okay, so I do it. Now, question is, what is this? Cosine, cosine, sine, sine, cosine y, cosine x, sine y, sine x.
Cosine ny minus
That's actually cosine ny minus nx.
nx.
Right? Good. So this is actually each of this term actually equals to cosine, okay, n y minus x. So that's good. Okay. So this can be further be replaced by from negative pi to pi fy. Okay, let's say 1 or 2 pi is outside. Okay, fy, and then multiplied by 1 plus 2. Okay, and from 1 to n, and then cosine n y minus x. Yes, dy. Everything's okay? Oh, let me just still put the square bracket over here too, not to incur any confusion. Okay. So again, the square bracket, and here is square bracket. Okay, square bracket. Everything is okay so far? Good. Okay. Well, what kind of function is this? Indeed, I mean, inside this square bracket, inside this square bracket, I can define this square bracket as certain function that, let's say, a k. Okay. Let's say this function is about k. Is a big function k. Then what is this function about? What is this function about? 1 is a constant. Cosine is a function. This function is only about y minus x. Right? This function is the value of this function is only y minus x. Okay. So I'm going to write the sum. Okay, I'm going to write this sum as k y minus x, or x minus y, doesn't really matter, x minus y, okay? And since, well, I'm having different choice of the big N, this function is also going to be different. So let me call it as kn. This is okay, right? Okay. So to be more specific, let me write it here again. I'm using kn x minus y, okay, to represent something that's called 1 plus 2 sum n flowing from 1 to n, okay, cosine n y minus x. Okay, right. So that's okay. Well, now, you see, now I'm having, now let's see what's inside this integration. I'm having a fy. Okay, I'm having a fy. I'm having a certain function that's about x minus y. And the function is about integration about dy. What is my goal? I wish this term converges to what? I wish this term converges to fx. I wish this term converges to fx. So let me write one more step. Let me write it one more step. So that means that I'm having 1 over 2 pi, okay? The integration from negative pi to pi, fy multiplied by k n x minus y dy. I wish this guy converged to fx. What does this remind you? What does this remind you?
The convolution.
Okay, so first of all, what is happening inside this integration? This is what? This integration is what? It's actually a convolution. Right, this is actually a convolution. A convolution between what and what? Convolution between what and what? Let's first ignore the integrand, right? From negative pi to pi, because the convolution that you are familiar with takes place from negative infinity to positive infinity. Right? Okay, but let's first ignore the integrand. Let's first ignore the integrand. I'm having something that's, so first of all, the integration is about y. And this is fy. And this is actually something that's convoluting my fy. The reason, there is actually a specific reason I call it as a k, because this is actually for kernel. This is actually for kernel. This is a kernel function convoluting with the fy. And I wish after the convolution I obtain exactly the same thing. So what do you wish? What do you wish that my Kn is? What
Sure.
function has the property that it convolute with any function, then we get the original stuff,
The other
the delta function,
That,
right? The delta function. We wish this guy to be the delta function. Okay, but okay, this is actually a very rough. This is actually a very rough argument because there are many technical details we haven't solved it yet. But I wish you to see the answer at first, and then we can sort out all these technical details. Okay. So first of all, again, this is a let me write what I said just down. Okay. So first of all, this is a convolution. This is a convolution. Okay, convolution on negative pi to pi. And what are the two parties of the convolutions? They are, first of all, the fx, and then another kernel function, knx. Okay? This is essentially the convolution between, okay, so there's another 1 over 2 pi. There's another 1 over 2 pi, but it's okay, it's just a constant. Okay? So it's fx convoluted with knx. Okay? And I wish, after the convolution, okay, this guy converges to fx, which means that this guy, okay, when n is finite, when I'm not taking infinite many Fourier terms, this will not going to be exactly the fx. But what we wish is that when n becomes larger and larger, my knx, the kernel function, will bring my fx closer and closer to itself. Right? So we wish. So, okay, we wish my k 1 over 2 pi, okay, kn x, we wish this guy to converge. Okay, we don't know what does it mean by the converge here because again, delta function is not a function. I don't know. We don't know yet what does it mean by converge to delta function yet. Okay, we don't know what is that, but we sort of wish this guy to converge to a delta function. But again, this is not going to be delta x. It's actually, let me call this guy. This is okay. Let's say delta x. But this delta x, okay, this delta x is defined. My x is defined on negative pi to pi and periodic. Right? You see. Again, this convolution takes place from negative pi to pi. My f is a periodic function. And my k, the kernel, you see, every term of my kernel is cosine something. Of course, that this is also periodic from negative pi to pi. So this is one periodic function convoluted with another periodic function. Okay? So we are wishing the kernel to converge to a delta function, but this delta function is defined on a periodic space. Okay? So what is exactly the delta x looks like? The delta x, now the delta x, let me call it as the, let's call it as the delta or delta wx. Okay, let me call it as the delta wx. So my delta wx is exactly this. First of all, it has the property of delta function, which means that it's 0 from negative pi to pi. Okay, it's 0 from negative pi to pi everywhere, but it is infinity as 0. Okay, it is infinity as 0. And don't forget, this kernel, okay, this kernel is what? It's a periodic function. So the infinity, we should expect the infinity to do what? To repeat every 2 pi. We expect this infinity to repeat for every 2 pi. So, which means that we hope the delta wx to be something like this. Okay, here is 2 pi. And here is 4 pi. And here is negative 2 pi. So on and so forth. Okay, we wish the okay, we wish the infinity to repeat every 2 pi because again, this kernel function is a periodic function. Again, we don't know it yet. We don't know it yet. But we wish this is true. We wish this is true. Okay? Well, okay. Well. you see that is true? Okay, how do you see that is true? So first of all, you see, what is exactly my knx? What is exactly my knx? My kn x minus y, my kn x minus y is 1 plus 2, and 1 plus 2 multiplied by the sum of the cosine functions, and y minus x, right? So replacing the y minus x by x, what do I have? What is my knx? What is my knx? My knx is actually 1 plus 2, the sum, okay, n from 1 to n, okay, cosine nx. Well, actually, cosine negative nx. Cosine negative n is exactly as the cosine nx. So I'm going to simply just say this. Okay, 1 plus 2, sum from 1 to n, cosine nx. Okay. Again, I want to show that this guy. I want to show that this guy actually converges to my delta omega x. Okay. Well, actually, I have a coefficient of 1 or 2 pi, so actually 2 pi. 2 pi multiplied by delta omega x. So far so good? Okay, so far so good. How do we show that? How do we show that this is indeed true? How do we show that this is indeed true? Well, first of all, what is the most important property of a delta function? Besides the infinity stuff, what is the most important property of the delta function? What is the integration of a delta function? 1. But that was when we were integrating from negative infinity to positive infinity, right? Now the delta function is only defined on the periodic space. So now I should expect from negative pi to pi, right? I should expect that from negative pi to pi, my delta omega x, I wish this guy, the integration to be what? I wish the integration to be 1, right? Okay. Now what is the integration of knx? What is the integration of knx from negative pi to pi? What is the integration of knx? Well, 1 is going to contribute as what? Because I can integrate term by term. This is not infinity. Right? I can integrate term by term. So the integration of first one of 1 from negative pi to pi is going to give me what? 2 pi. Okay. It's going to give me a 2 pi. What about the other terms? What is the integration of cosine x from negative pi to pi? What is the integration of cosine x from negative pi? What is it? 0, right? Because it is pure, it has a period. It has a period of 2 pi. What about cosine 2 pi, cosine 3 pi, cosine 10 pi? What about their integrations on negative pi to pi? Still 0, right? So it's going to be 2 pi, and then plus 2 multiplied by 0 plus 0, blah, 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 blah. Okay? So actually it's 2 pi. Well, don't forget, what is the right hand side? We wish the right hand side is 2 pi multiplied by delta omega x, right? So, and as we say that, as we have just argued that, we wish the integral of delta wx, okay, should be 1. So indeed, we say indeed, we have shown that the integration of the integration of knx is indeed 2 pi x, which equals to 2 pi, okay, multiplied by the integration of delta wx. So this is only the first step. We have only verified that the integration of these two terms are the same. Okay, we have only verified that the integration of these two kernels are the same. Okay, we have only argued this. Well, but this is not finished. This is not finished yet. Well, now we propose to compute knx more directly. Again, kn equals to 1 plus 2, sum from 1 to n, cosine nx. Okay. Again, this seems to be rather hard to do the sum. Right? This seems to be rather hard to do the sum. But we can argue that this can be done in a very smart way. okay, in a very smart way. Don't forget the Euler, don't forget the Euler's equation. Okay, which is that e the I theta equals to what? What is e the I theta?
Cosine theta.
Is cosine theta and then plus I sine theta, right? So I can safely say that cosine nx equals to what? Cosine nx equals to e the I theta plus, e the I nx and then plus e the negative I nx be divided by 2. So what's good? So what's good? So what is this? This is essentially, okay, 1 plus 2 multiplied by the sum n from 1 to n, e the I nx plus e the negative I nx, okay, be divided by 2. 2 and 2 cancels. So this is essentially the sum, okay, sum n from negative n to positive n, okay, e the I nx, because e the 0, I 0x is exactly what? Is exactly 1. Is exactly 1. So far so good? So far so good? Well, what is this? What is this sum? What is this sum? This sum is actually a geometrical sequence, right? This sum is actually a geometrical sequence. Well, do you see that is true? Do you see that is true? Because of what? Because this is actually what? This is actually okay. So e the negative I nx and then multiply by 1 and then plus okay e the I e the I x and then plus e the I x squared and then plus e the I x cubed and then until e the I x the 2n times. Right? Right? This is actually a geometrical sequence. This is actually a geometrical sequence. And since this is a geometrical sequence, we can very quickly write down the answer. Okay? We can very quickly write down the answer, which is exactly e the negative I n x, okay, minus e the I n plus 1, okay, x, okay, over 1 minus e the I x, okay, e the I x. And okay, this actually we can so here actually we can multiply a e the so one last step. Okay, one last step. We can multiply e the negative 1/2, okay, ix on both sides. Okay, e the 1/2 on both sides. Then the top becomes e the negative I, okay, n plus 1/2 x minus e the I n plus 1/2 x over negative e the let me see, okay, negative e the 1/2 ix plus e the negative 1/2 ix. Okay, so again using the Euler's formula, the top is actually sine n plus 1/2 x. Okay, the below is exactly sine 1/2 x. Here. So suppose, oh wait, can you see how to get from here to here directly? Do you see how to get from here to here directly? This is again because of the Euler's formula, right? E the I n plus 1/2 x actually equals what? Equals to cosine. There's a cosine part. There's actually a cosine part and an I sine part, right? This has the minus of this guy is going to also going to have the same cosine part, but a I sine part with a different sign. Okay, so after the deduction, the cosine part goes away, and only the sine part remains. Okay, again, so just here, let me just write it down. This is here. From here to here, again, you just need to use the English formula. Okay, you just need to use the Euler's formula on both sides. Okay, on above the fraction line and below the fraction line. Okay, well, okay, if you are still confused, so again, for example, either 1/2 ix that equals to cosine, right? Cosine 1/2 x, and then plus I sine 1/2 x. Okay, either negative 1/2 ix that equals to cosine 1/2 x, and minus I sine 1/2 x. Right? So minus this guy plus this guy minus and now minus, okay, and then these two guys plus together, this guy goes away, this guy goes away, we are going to obtain a part that's only about sine 1/2 x. Okay? So, and the same reason for all the fraction. So that's good. So this is, again, what is that? What is that? Don't forget, this is my k and x. Okay, this is my k and x. And what is our goal? What was our goal? We wanted to show that my k and x approximate the delta function. We want to show that the k and x approximate the delta function, which means that there are two things that we need to prove. First of all, when n goes to infinity, this guy is 0 almost everywhere, and this guy is going to be infinity when x is 0. These are the two things that we do prove. Right? These are the two things that we do prove. Well, can you prove that is true? You can see what you can see is that this is actually not true. Why this is not true? Well, you see, this is because let's say I am fixing an x, right? I'm fixing an x, and what will happen above? What will happen above the fraction line? Whatever is happening above is that it's going to be sine n, sine 1, 2, 3, 4, 5, 6. Okay, so this kind of thing is actually going to oscillate up and down, up and down, up and down, and never converge to 0 because and the bottom is going to stay the same. Right, the volume is going to stay the same. The denominator is staying the same. And this guy is going to oscillate. So indeed, you see, there's actually no way for us to prove that in the function sense, right? There's no way. Let me write it down, this argument. Okay. There's no way to argue in the function sense that my kn(x), which equals to sine m plus 1/2 x over sine 1/2 x, this guy converges to delta. Okay, so actually 2 pi delta wx. Okay, there's no way to argue this in the function sense. Okay, there's no way to argue this in function sense. And the only thing that we can do is to argue this, in the way of inner product. Okay. Because of what? Because this is because the delta function, again, delta function is not a function. Delta function only makes sense when it is convoluting or doing the inner product, with another function. Okay. So here our goal is to show that we only need to prove that. See, you see, because I want to show that my Snx, oh sorry, it should be actually, it's my Fnx. My Fnx, converges to Fx, right? So actually, let me take the difference. Fnx minus fx exactly is, okay, from negative pi to pi. The kn, sorry, k is actually, okay, so that's actually kn x minus y, fy dy, and then minus fx. Okay, we want to show that this guy goes to 0. Right? We wanted to show that this guy goes to 0. So far so good? We wanted to show that this guy goes to 0. And what? And you see, oh wait, so wait a minute. So there were actually there was actually a coefficients. Okay, there was actually a coefficient. So what did I really give it? 2 pi, 2 pi. Oh yes, okay. Yep. So actually 2 pi is actually coefficient over here. 2 pi. Wait a minute. Sorry, it's actually. Sorry, I got myself wrong. There's no 2 pi over here. There's no 2 pi over here, but here we're actually having a 2 pi, 1 over 2 pi over here. Yes. Okay. Now it makes it right. 1 over 2 pi over here. Okay. And what do we just what do we just do? Okay, you see, we have already shown that, okay, so first of all, we have already shown that the integration of from negative pi to pi kn x, okay, this guy px, this is essentially 2 pi. Right? We have shown that this guy is essentially 2 pi. And this is the first thing. And second thing, you see, the convolution kn convoluted with f, okay, knx convoluted with fx, this can be written as either from negative pi to pi kn x minus y fy dy, right? But this can also be written as from negative pi to pi kn x, let's say kn y, and then fx minus y dy. This is okay? So far so good? This part is okay? And so, okay, so therefore combining these two things, I'm first going to do the following. I'm first going to say that, okay, fx, first of all, fx equals to 1 over 2 pi multiplied by 2 pi multiplied by fx. Okay, I'm basically doing nothing but simply introducing a 2 pi. Simply introducing a 2 pi. And what is 2 pi? Well, 2 pi, you see here, 2 pi is exactly the integration of the integral, right? The integration of the integral. So this is actually 1 over 2 pi, okay, multiplied by the integration from negative pi to pi, and then kn y dy. Well, I can simply put the fx inside, okay, dy. Is this okay? Is this step okay? Because you see, when you are doing the integration, the fx is actually a parameter that comes out, and then the rest of it is going to do the integration, right? Then we already know that the integration of this is essentially the kn. The integration from negative pi to pi knx, okay, that is 2 pi. Okay. So now combining. Now let's say I am putting the representation of fx over here, okay, back to this equation. Now what I obtain is, okay, fnx minus fx is actually 1 over 2 pi, because you see, 1 over 2 pi from negative pi to pi, okay, kn y, and then fx minus y multiplied by, minus fy dy. Okay. So again, what is this? So This is the, I'm having, so the first term is the convolution of between my Kn and F. Okay? And what is the second term? The second term is that, well, you see, oh, sorry. I made a mistake. I have made a mistake here. So the second term is actually should be Fx. Should be Fx. Sorry. Okay. And the second term, again, you see, the first term is the convolution, right? First term is the convolution, which is my f and x. The second term is this guy, integration on y. Okay, we're going to get 2 pi. And 2 pi, 1 over 2 pi is going to cancel, and fx will stay. Because this is nothing about 1, right? So stay, we're going to get x. Okay, so this equality will still hold. And so you see, what we are having over here, is, okay. So let me put. Okay, so wait a second. So yes, okay. And don't forget. What is my Kn? We have already computed our Kn, right? Here. We have spent some efforts. To compute our Kn. So don't forget that my Kny is exactly sine, okay, m plus 1 over 2 y over sine y over 2. This is my Kn. So put this back over here. What we're having is this. Okay, so 1 over 2 pi. The integration from negative pi to pi, and now this is what? Let me see. This is actually okay. So this is actually f x minus y minus fx. Okay, and then over sine y over 2, and then multiply by sine. Okay, n plus 1/2 y dy. Okay, from here to here, I'm just simply replacing the Kny by sine n plus 1/2, 1 over 2y over sine y over 2. Okay, and here I'm just simply combining this guy and with 1 over sine 1 over 2 at first, and then leaving the sine n plus 1 over 2y outside. This step is okay. Okay. I know this is already very tiring, but I promise you this is the last step. Okay, I promise you this is the last step. Why this is the last step? Well, now, okay, I'm going to pack this up. I'm going to call this guy to be, because you see, now let's say my x is fixed. Don't forget, now my x is fixed. F is anything, but x is fixed in our case. We are arguing that f and x is converging to fx. Right, but f is fixed for now. Pointwise convergence, f is fixed. So f is fixed, and let's say here. So this function, I can call this function to be a b. Let's say g x y. Okay. So this function is a function of y, but parameterized by x, because when x changes, this function also changes. Right. This is a function of y, but parameterized with x. Whenever I fix my x, this function is fixed. So that's good? This function is fixed. Okay, then what is this? What is this integration? This integration is what? This integration is what? It's actually the inner product between gx and sine m plus 1/2 y. Is that right? Mm-hmm. Is that right? Okay. So again, this is actually 1 over 2 pi, the inner product between gxy and sine m plus 1 over 2 m plus 1 over 2y. This is okay? This part is okay? Mm-hmm. Okay. What is sine n plus 1 over 2y? Well, it's not so direct to obtain what is 1 sine 1 over 2y, but if we refer to what we have done the last time, if we refer to what we have done the last time, let me see here. Is that in this place? Generalized Fourier transform. No, I think here. What is this? Now, don't forget, my L equals to pi. Okay, my L equals to pi. So here, you see, when L equals to pi, sine, this Fourier series was sine 2k plus 1 pi x over 2L. And that is exactly sine 2k plus, sine k plus 1/2 x. So that's a bit? So this is what? Sine k plus, so actually we were using n, we were not using k, using n, but this doesn't really matter, right? So that's actually sine n plus 1 over 2x. What is this? What is this? When n goes from 1 to infinity, this actually is a series of what? This is a Fourier series, corresponding to what type of boundary conditions? One side is Dirichlet, another side is Newman. But if we don't care about boundary condition, this is what? This is actually a Fourier series. Right? This is actually a Fourier series. If this is a Fourier series, then going back to going back to our this one. Sorry. Here. Why am I always keeping how to be? Here, okay. Again, this is a series of Fourier series. This is actually a Fourier series. Why? Right? What is the inner product between a function and a Fourier series? Is the Fourier coefficients. Right? This is the Fourier coefficients. This is exactly the Fourier coefficients. Right? This is exactly the Fourier coefficients. Okay, between coefficients. Okay, between gxy and sine n plus 1/2 y. Okay, so far so good. And according to what we have just learned in 5.4, okay, according to what we have learned in 5.4, okay, what do we know about the Fourier coefficients? What do we know about the Fourier coefficients? What do we know about Fourier coefficients? According to the Parseval inequality, first of all, the sum, okay, first of all, when n goes to infinity, okay, here, an is the Fourier coefficients, right? This is the true norm of every Fourier term. This is the true norm of the function itself, right? So that means that when we are summing towards the infinity, we know that, okay, the sum of this goes to a fixed number, which is the true norm of the function itself. So as long as the function has a finite true norm, right? As long as this function has a finite true norm, what do we know? As long as this function has a finite true norm, then you see this is a sum of infinite many things, but all of these terms are what? Are positive. This is a infinite sum of positive terms, and they converge to a finite, and their sum is finite. So what can we say about every term? What can we say about the tail of the series? It can only become smaller and smaller and smaller and smaller, and finally goes to 0. Because if it doesn't go to 0, then its sum cannot be finite, can never be finite, right? Therefore, okay, according to, okay, here. So here, according to the Parseval equality, okay, according to the Parseval equality, okay, the inner product between gx, y, okay, and sine n plus 1/2 y, okay, this guy over the true norm, wait a minute, okay, sorry, this guy is the, this guy, okay, it has to go to 0, pending the verification that the true norm of gxy, okay, the true norm of gxy is finite. Okay, pending that the true norm of gxy is finite. So that's good. Well, why do we need the true norm of gxy is finite? Because this is because again, let's go back to the theorem over here, right? You see, again, if the right hand side is infinite, what will happen? If the right hand side is infinite, if the f doesn't have a finite, if f doesn't have a finite, if f doesn't have a finite true norm, what will happen? Then this side is going to be infinite. Then this is an infinite sum, and finally goes to infinite. Then we cannot conclude that okay, this guy is finite. Then we cannot conclude that this guy goes to 0. Right? We cannot conclude that this guy goes to 0. So again, going all the way back to what we have over here. Okay, this is the Fourier coefficients, and the Fourier coefficients, okay, will go to 0, pending that the gxy is has a finite true norm. Okay, gxy has a finite true norm. Well, does it have a finite true norm? You see, okay, so what is the true norm? Okay, what is exactly the true norm of gxy? So gxy, the square of the L true norm of gxy is exactly from negative infinity to positive infinity. Don't forget what's the definition of g. What is my definition of g? My definition of g is actually fx minus y minus fx and over sine y over 2, right? So this is actually x minus y, okay, minus fy over sine y over 2. Okay, this guy is squared dy. Okay? How do you show that this is indeed finite? The integration is finite. How do you show that this integration is finite? Because again, this is indeed really a last step, right? After we can confirm that this guy is finite, this integration is finite, then my gxy is what? Is an L2 finite function. Then, because the inner product, this inner product, are exactly the Fourier coefficients of a L2 finite function, then this Fourier coefficient, they can only goes to 0. If they indeed if the Fourier coefficients goes to 0, then that means that my fx indeed goes to fx. Then we have already proved. Then we're already done with our pointwise convergence, right? So everything depends on our last step. Is my gxy a L2 finite function? Is that obviously, absolutely a L2 finite function? Is that right? Is that absolutely an L2 finite function? It might be, but you see, the trouble is that we're having a sine 1 over 2 in the fraction on the fraction line. And my sine 1 over 2 can be what? It can be 0. So that actually is indeed bringing us trouble. Right? That is indeed bringing us trouble. But, you see, what do I know about f? What do I know about my f? Sorry, here is not y. This is not y. This is actually not y. It's actually x. Sorry. Here, let me check. Yes, sorry. Here is fx. Sorry, my bad. This is fx. So you see, what would happen? So first of all, between negative pi and pi, when will my y goes to 0? When will my sine y goes to 0? Y is 0, right? But if my y goes to 0, here, what can I say about fx minus 1 and fx?
0.
This number also goes to 0. So actually, it's actually a 0 be divided by 0. And then that depends on what? That depends on what? That really depends on, first of all, if my f is continuous. And then second, if my f is what? First order differentiable. Right? Because if my f is not first order differentiable, then what? If my f is continuous but not first order differentiable, then okay, this guy doesn't have to be a finite number or doesn't have to be a fixed number. It's still arguable. But luckily, what do I know about my f? What do I know about my f? What was the assumption at the beginning when we were proving that okay? What was at the beginning that when we were proving for the pointwise convergence, fx is a C1 function. Fx is continuous and it has continuous derivative, first order derivative. Therefore, we can say that when y goes to 0, okay, when y goes to 0, fx minus y minus fx, okay, over sine y over 2. This is actually going to what? This is actually going to negative 2 f prime x. It's going to negative f prime x. You see, my f prime x, okay, you see, this indeed requires my f to be differentiable everywhere, right? Because you see, x here is arbitrary. F is arbitrary. If f is not differentiable at certain places, then that means that, okay, this guy doesn't have to go to a negative 2 f prime x, which means that, okay, this guy, the integration of this integration, it doesn't have to be finite. Again, if this integration is not finite, then I cannot conclude that the Fourier coefficient goes to 0. If the Fourier coefficient doesn't go to 0, then I cannot conclude that, okay, my fnx goes to x. So it concludes everything. Okay, this concludes. So now we have successfully done the proof. This is successfully done the proof for pointwise convergence. Okay, this is a proof for pointwise convergence, and we need one more, probably another half lecture to complete the proof for the uniform convergence. But that's it. Okay, that's it for today. This is indeed a lot to chew up. Okay, and they connect many of the. This is actually a very. This is actually even a 3-page proof. Okay, on our textbook, and it's actually the main one part of the main materials for 5.5. And I wish you could refer to. I wish you to go through all the technical details by yourself again. Okay, after the class. Okay, to make sure you really can connect everything that we have learned. Okay, to the proof over here. Okay, thank you very much.
你知道这个是？我正要问，你去问他。